All right, everybody, this is the 3.7 lesson, all about iPhones, and and specifically, it's giving you data here of the iPhones that came out in these years and how many they sold on opening weekend, just opening weekend. So way back in 2007 was the original iPhone. They sold 500,000 in the first weekend. Then in 2015. The 6S Plus was the latest, and they sold 13 million iPhones in the first week, the first opening week. Crazy, huh? So we're going to take this and we're going to analyze it. Don't do the names of the phones, just this, using two quantitative variables on the applet. I've already actually sketched this, but I'll show you how to get it. Um, I have already done this. I took time to put the numbers in there. Notice I did the entire year, full 2007, 2008, and so on. All right, and then you hit begin analysis, and there you have it. I already copied and pasted this into my notes. You can definitely take some time right now, pause the video, and put this data in yourself so that you can follow along. Okay. You'll notice as you look at this, it does not look linear to me, okay? The scatter plot to me looks like it's curving, right? It looks to me like it's quadratic, which is the form is not linear, perhaps quadratic is what I'll say, okay? Perhaps quadratic, question mark? You know, quadratics are parabolas, and to me, it looks like the right side of a parabola, the right half of a parabola. Number 3, use the applet to find the least squares regression line and write the equation. And to graph it on the scatter plot. Easy enough. So, zoom back out, just got to hit the buttons. So there we go. There's the line. And notice it doesn't really hardly catch any dot cleanly. So it's not a very good fit. Down here's the equation. I'm going to transfer it over to my notes. I might just, no, I'll write it. Okay, I'm going to write it in context though. I'm going to say iPhones sold equals negative 3,222.6 plus 1.605 per year. And I'm going to remember this little hat. Because remember what that hat means? It means the predicted number of iPhones that I'm selling, okay, is based on the year. All right, and then you can try to sketch it, but it kind of did something like this, right? Maybe it was a little. You can screenshot it if you want, but it was something like that, I believe. Okay. Um, it's not a very good fit. Um, when you made the least squares lines of regression, right here, that when I made the line, a new graph was shown underneath the scatter plot. It was the residual plot. So let's go screenshot that and put that in the notes. They're talking about not the top one is the scatter plot, but the second one says residual. I'm going to screenshot that one, put that in my notes right here. Okay, what this um, is a graph that shows me the residual for all, 10 dots, or however many dots I've got. Okay, if I can stretch it out a little bit. Maybe scooch it over. I'll do that. And then I'll take the easy way out and just put white over that. There we go. So there's the residual plot. Okay, every dot, like so this dot is this dot right here. It has a positive residual. This dot would be the fourth dot. That would be that dot right there because it is below the line. It has a negative residual, okay? What I see here, and is the big takeaway, is that this plot, oh boy, I forgot to shrink the pen. This plot has a curved or smiley face pattern, right? I say that the scatter plot up here was curved, and when I made a residual, it was kind of like a leftover curve. It's still curved, leftover curved pattern. Okay. So what that means, when that happens, you need to understand that a linear regression, a linear model is not the best choice. Okay. Um, Let me show you this. I'm gonna screenshot this residual plot and kind of make a connection for you. Copy that. I'm gonna come up here. I'm just gonna paste it over here on the left, right on top of my. Okay, so there's my residual on the left and my scatter plot on the right. If I just tip this sideways and kind of scoot it over, do you see that the residual plot on the left is pretty much this same one as the scatter plot? It's just turned, pivoted at an angle like that. So like if I leave it like this helps you see it. The zero line is the same as the line of best fit. To me, that was kind of like a light bulb went off when I saw that, right? These two dots are these two dots, okay, because they're above the line. So hopefully that helps you see what's going on a little bit. Okay, so here's something cool. Number 5, we're going to go back to the applet and we're going to run a quadratic regression, not a linear regression. And then we're going to compare the residual here to the residual of the new one. You do that by right down here, it says calculate the other type. Ooh, weird, what happened there? Right here, quadratic, and then click calculate other regression. So when you did this, maybe it's hard to notice, but it gave you the new equation, and right above it here, this is a new residual plot. It is different. I'm going to screenshot it, put it right in my notes right next to the other one, okay? Okay, so there's that one. Doesn't fit too well, so I don't like that extra stuff over here. So I'm getting rid of it. Okay. So I've got them one on top of the other, okay? Now this one, this has no leftover curve, right? The scatter plot was curved. This one is not curved. Another way to say it is like no pattern. Or you could say equal scatter. There's really no pattern going on here whatsoever, right? I've got a couple above, a couple below. Like I couldn't, like there's nothing going on there, right? I can't draw a smiley face. Likewise, I can't draw a frown. There's no leftover curve, okay? And that means that this is a better model. Could put a star by this. This is a better model. And let me give you some metrics. Well, I can't spell. Let me give you some metrics about why it's a better model. You can get all of this information from the applet, okay? Just right here in the boxes, right there. They have S and R squared for both. So just transfer those over to the notes. Okay. I've got them written down here. I don't have that good of a memory. I'm cheating. I'm taking the easy way out. Okay. And there you go. All right. So, what does all this mean? This S is new. Okay. S is the standard deviation of the residuals. Okay. So so all these dots, these are the residuals. This one's really small. This one's, these all have a value. In fact, if I go back to my applet, they give me the values right here. This last lowest plot is a dot plot of the residuals. Okay. Um, and if I get the standard deviation of them, that's S. Here's a way to say it that might make more sense. The iPhones sold is typically about S, whatever S is. So typically about 0.676 million, because this is in million away from the predicted sales. Okay, because the predicted sales, let me see if this helps. If I had a dot right here, that has a residual of 0, meaning it it's the number of iPhones sold that year matched the prediction perfectly. Okay, and so this S is essentially giving me the standard deviation of the residuals. It's a deep thought, I guess. Okay, um, but look at these two numbers, right? 1.4 versus 0.676. This is telling us that the quadratic model is much better because the iPhones in this model were only off by about 0.6 million. And if I do a linear model, that means on average, my dots will be 1.4 million away from my prediction. That's not good. I want a better model will have a smaller S, a smaller standard deviation of the residuals. And if it's a smaller standard deviation, these dots will get closer to the line. Okay. And then they both give you R squared. R squared is something else we need to discuss. It has a slightly different meaning. Okay. R squared has a name, coefficient of determination. Sounds very serious. Very serious. Okay. Here's how you would interpret the 98%. Okay. First of all, you change it to a percent. So 0.98 is 98%. 98% of the variability of iPhone sales is accounted for by our model, by the quadratic model. Okay, which is good. The higher the percentage, the better. You want to be able to account for all of the variability from year to year to year. From way back up at the top, from 2010 to 2011, there's variability. You want your model to accurately predict that increase from 2010 to 2011. So the higher R squared is, the better. There are some phrases that come up a lot. Is accounted for um, can be replaced with, here's other phrases, can be explained by. You might see that one sometimes. You might be is attributed to. That's a lesser known one, but you might see these phrases any one of these 1, 2, 3 phrases, okay, for r squared. Okay, so I've thrown a lot at you. Let me just try to summarize what's going on here in our quick notes. So, number one, when you have residual plots, okay, you can have it, whoop, that's not straight, that's going uphill. Residual. Okay. So I'm going to do two of them. So I'm going to just copy this one and put it right underneath it. Okay. So if you have a residual plot that is a good model, you're just going to have scattered dots in a random pattern, like some here, maybe here, right? This is a good model. Okay. If you had something that made a frown, something akin to a frown or a smiley face, this is a bad model, meaning that you should do a different type of regression. Maybe from linear, you could switch to exponential, okay? So I guess this would be equal scatter, no pattern is another way to say this, equal scattern. Okay, number two. Number dos. What is S? Just a refresher, it is the standard deviation of the residuals. Okay. If your residuals are on average very small, very close to zero, S will be small. The goal is a low S. Okay. Here's how you could say it. The actual Y variable, how you could say it in context, is typically, or typically is another word for on average, typically about S away from the predicted Y value. Predicted Y variable. Here, I'm going to switch the order here. Just sits with my brain better. I'm going to do this. From the Y variable predicted by the model. Okay, in other words, the model is predicting what we think it will be, and then in reality, the actual numbers are very close if S is small. If S is large, then on average, our actual numbers are varying a lot from our predicted values, and that's not good. So you want S to be small. A small S is a sign of a good regression model. All right, number three, R squared, what was it called again? The coefficient of determination. Okay, and here's what it means. R percent, R squared percent, sorry. R squared percent of the variability. This is kind of a repeat, but it just is really good to write it a couple times to get it memorized. Okay, R squared percent of the variability of the Y variable is accounted for by the model. Um, your goal here, your goal for r squared is r squared close to 1. Because if r squared was 1, then here you'd be saying 100% of the variability of y is accounted for. In other words, we're 100% confident, okay? And that would be fantastic, all right? We won't ever really get that. Okay, hopefully that helps. I think I'm done here. Thank you. Bye-bye.